อ้ปะตามสบายครับก่อนคือ
ไม่ออกเลยไม่ได้ยังไงว่าของที่จะเอาไปใส่เลย
Good afternoon, everyone. Welcome you to SCI33206 Section 4 M604 อันนี้ที่ผมแล้วก็กิจภูทิพย์โอเคแล้วก็พาราหายไปแล้วพาราย้ายไปอยู่นู่นแล้วกันตะกรครับโอเคครับแล้วก็ศิลวิทย์สุขีนะครับแล้วก็รวิพลมานี่นะครับ พิมพ์สินจะอยู่ทางไหนเอ่ยพิมพ์สินฮัลโหลไม่เจอนะครับเต็มเมืองครับพี่นับครับก็พิชานันท์โอเคพัดไทยคิงครับศิลวิทย์โพขีดไปไหนแล้วทีแล้วก็ธนวิทย์ครับโอเคแล้วก็สดุดีครับแล้วก็รัตนะศิวกรครับศิวกรฮัลโหลศิวกรนัทพลแอลแล้วก็ชยุทธพลครับชยุทธพลอยู่ไหนเอ่ยชยุทธพลกรครับอภิโชติครับชานนท์ครับกมลสิทธิ์นะแล้วก็สุภรัตน์อยู่นู่นนะณัฐพลเอ็นอยู่นู่นนะยิ้มสินครับแล้วก็ศิลวิทย์โพขีดยังไม่เจอนะครับพามครับพามนัทธดลครับ อยู่ไหนเอ่ยยกมือโอ้บังอริยวุฒิอยู่นี่ภูริศักดิ์นั่งใกล้ๆกันวัฒนพัฒน์หายโอเคเหลือศิลวิทย์โพขีดคนเดียวOkay, let's continue our lecture on the standard model of elementary particles. We can see that there are two main groups, such as fermion and bosons, right? And you have quark and leptons, and for both quark and leptons, we have the antiparticles. Okay, you just put mostly you just put the word anti, the prefix anti, in front of that particle name. For example, if you have up, you're gonna have anti-up particle. Okay, the mass is the same, but the charge is in opposite way. The spin number is also the same. The difference between the fermions and the bosons is that all fermion would have the spin number as 1/2, but the boson would have the spin number as 1 or 0. Okay, that's the elementary particles for everything in the universe as the physicists just discovered it. Let's talk about a specific particle that is quite important for us in the high school level, and that's the proton. Right? Proton has 2 quarks and 1 dark quark, and all these particles are combined by the gluon, which is the zigzag symbol that's called gluons. Okay, gluon just is like the word glue. Okay, but this one will work as the combining element. Okay, that joins. The joints are up together, and this will form the so-called proton to us. As you know, from the main particle, the up quark has the shadow of 3 by 2, right? One down quark has a shadow of 3 by 2 of the electron, and the one down quark has the shadow of 1 minus 1 by 2. Okay. So is that correct? One down quark would has the shadow of 1 by 3. Sorry for that. 1 by 3. And this one is 2 by 3. Okay. When you want to determine the charge of the proton, because you have 2 of quarks, so charge of proton will be 2 twice. Okay. The value of a charge of up quark, which is 2 by 3, and then you're gonna have plus the charge of 1 down quark, which is minus 1 by 3. Okay. So you get 4 by 3 plus or minus 1 by 3, and that will be 3 by 3 or no. And that's why you have one positive charge for the proton. Okay. This is the way to determine the charge of the proton. Let's move to the neutron. Okay. Neutron has something very similar to the proton. Yeah, it has also up and down quark, right? But the number of quark reduces by 1, and that particle changes to down quark. Okay. This is proton. Okay, proton. And for neutron, you're gonna have 1 up quark, right? Up quark has the charge of 2 by 3, and 1 down quark has the charge of minus 1 by 3. When you are to determine the charge of the neutron, you're going to need to combine, because you have only 1. This is 1, 2 by 3. And plus, because you have 2 down quarks, right? Number 2 and minus 1 by 3. Here you would have 2 by 3 and minus 2 by 3. So you will get 0. And that's why we don't have the charge for the neutron. The neutron acts as the neutral stuff, neutral particle. It doesn't have charge at all, so the charge remains 0. This is the reason. Okay. I think that no one is going to give you the detail in the regular high school physics. But if you go into the deep detail, you can see the reason why we get 0 charge for the neutron. Okay, now let's move to the next thing. And that's the wave particle duality. Louis de Broglie, right? Louis de Broglie is a guy who studied in Paris, I think. Okay, this is how he looks. This is how he looks. Okay, the boy studied in a famous university in Paris. Okay, so it has a big impact. Okay, he didn't make any experiment. He just used his brain to think about it or imagine how the thing should go in nature. Okay. In 1924, a French physicist, whose name is Louis de Broglie, he postulated, of course, that it's not the truth, it's just what he imagined. Okay, and the big advantage when you study in a famous university or high impact university is that many people are going to believe what you say. Okay, and one of the cases is Louis de Broglie. He postulated that a free electron with mass m with the free electron it doesn't have any binding or covalent bond with any nucleus. So if this electron moves with the speed v, it's going to exhibit the wavelength lambda. So according to the classical momentum theory, you can have the momentum for that electron as P equal to mv, right? So this P is the product between the mass of the electron and the speed of the electron, right? This is exactly the same as the photon, and the lambda of this wavelength can be found from lambda is h by p. So he got the variation from the Planck constant h, okay, and divided by p. So p is mv, right? So we have m, which is the mass of a particle, and v, which is the speed of that particle. Please note that when the mass is quite large, that particle cannot move quickly, right, with very high speed. And when the particle is so small, smaller and smaller, it can get higher speed. It can move very quickly. Okay. He asserted that this relation holds for many things. For example, electrons, protons, and all other particles. Now let's try to practice ourselves in order to get familiar with the Broglie formula, right? The Broglie formula. The mass of a neutron, of course, is 1.675 times 10 to negative 27 kilogram, which is very, very small. Please find the speed of the kinetic energy of a neutron that has the Broglie wavelength of lambda equal to 0.2 nanometer. Nanometer means 10, the prefix of 10 to negative 9, right? Let's get back to this formula. We know lambda, we know the Planck constant, we know the mass of the neutron, right? Neutron is the object of the particle that we pay attention to. If we want to find the speed, we need to move v to the left-hand side, and lambda will stay in the place of the v with the speed. So v will be h by m lambda. So v is h by m lambda. Of course, the Planck constant will be 6.6 times 10 to the 34 joules per second. The mass of neutron is available here in the SI unit, 1.675 10 to negative 27. And you need to convert the Broglie wavelength from nanometer to the SI unit, which is meter, 10 to the 9. After the calculation, you're going to get 77 meter per second, which is that high speed or low speed? What do you think? is quite fast, right? Is there anybody who can run with this speed? Almost 10 kilometers, 2 kilometers in 1 second. มีใครวิ่งได้2กิโลเมตรใน1วินาทีมีไหมครับมีเหรอคุณทำได้เหรอเอาถนนตีเพชรให้ผมดูหน่อยเดี๋ยวผมปิดบอกจราจรมาตั้งกลวยดูให้ผมอยากดู1วินาทีคุณได้จริงเหรอนิวตันทำได้ครับประมาณ2กิโลเมตรมันเป็นไปได้ยากมากของใหญ่ที่จะวิ่งเร็วใช่ป่ะต้องของเล็กๆอย่างนี้ครับ Only 1 second this neutron can cover 2 kilometers. Let's talk about the kinetic energy. Of course, kinetic energy is the can be derived from the basic formula, right? It's 1/2 mv squared. Okay, that's the basic thing. But you need to give the detail to a particular particle, which is neutron. The mass of neutron, v, which is the speed, which is what we got before, which is 1977 meter per second, right? So here you can get the kinetic energy of that neutron in terms of joule, which is not actually is very hard to detect, but it still is 3.27 10 to negative 21, which is very little. But in order to be more appropriate, we're gonna change the unit of energy from joule to a more appropriate unit, which is electron volt. Okay, we're gonna divide this energy in terms of joule by the sharp value of the electron, and that energy will be called electron volt. In terms of electron volt, the neutron will have the energy of only 0.02 eV, okay, electron volt. Let's talk about another example. We consider something bigger and can be found in our daily life. For example, baseball. Baseball is the ball, but it's not quite. It's not easy to find in Thailand, right? หาได้ง่ายไหมลูกเบสบอลเบสบอลเป็นยังไงขนาดไหนผมก็ไม่ค่อยรู้เลยผมรู้เทนนิสใหญ่Apple ใหญ่กว่าเทนนิสใช่ป่ะใหญ่กว่าครับโอเค that's the size of the baseball. The first thing is the electron, which has the mass of 9.11 10 to negative 31. It moves with very high speed. It's 1 times 10 to 10 million meter per second. Oh, very fast. In 1 second, the electron can cover and take the distance of 10 million meters. What is that? 10,000 kilometers. Okay, 10,000 kilometers. That's the distance of this electron can cover. And another molecule, which is baseball, which has the mass of 0.145, and it is pitched at 45 meters per second. How fast is that 45 meters per second? In 1 second, it can cover the distance of 45 meters. So not so much, but it's acceptable, right? Yeah, it's acceptable because the guy who play in baseball game needs to put much force, right, in order to throw the baseball. Okay, 45 meters. So you need to compare the ball wavelength from electron and the wavelength from the baseball. Then we're going to see. So lambda is h by p, MP is MV, right? Mass and velocity. For the electron case, you just substitute a Planck constant and mass of electron, velocity of the electron. You're gonna get 7.27, 10 to negative 11, which is very small. I think human still doesn't have any measurement device to measure this distance. The next one is the wavelength for the baseball. Baseball has a bigger mass, greater mass, and lower speed, only 45 meters per second. Then you put it into the tablet and you get 1.01, 10 to negative 34 meters, which is even much smaller. Okay, so we cannot detect the wavelength from the baseball movement. Okay. This one is even easier to detect. And this one is impossible. Okay, the wavelength from the baseball. The second problem is tricky. Okay, we cannot solve it in a typical way, in the conventional way, because now the particle has a speed. Yeah, what is the question? The question is compare the wavelength with that of an electron traveling at 0.999 Z. So what is Z? Z is the speed of the light, right? So 3 times 10 to 8 meters per second. Well, you can see that the scaling factor 0.999 is very close to the speed of the light. It is close to the number one, right? So totally, the speed of this electron is pretty very high and very close to the speed of the light. Okay, but from the theory, any particle cannot move faster than the speed of the light. Okay, you cannot use the typical formula for the moment of computation. You're gonna need to use something spatial, and that the relativistic momentum. It's available in the book number 1, equation 26.5. You just P is MV, but you just have another scaling factor, which is 1 by square root 1 minus B by C. Okay. What is that then? If you have the speed very close to the speed of the light, let's say if V is Z, C by C will be 1 square will be 1. 1 minus 1 will be 0. So momentum of the light is infinity. Okay, this MC divided something divided by 0, so it's going to be infinity. This is called relativistic momentum. You need to use this formula because the speed of the particle is very close to the light speed. Now, let's compute the speed of the wavelength from that high-speed electron. This is P, right? P with the scaling factor, and you change the speed to the speed of the electron, and you flip it. It's going to stay at the numerator. Now it's time to substitute everything. This is the Planck constant, the mass of electron, the speed of the electron, which is very close to the speed of the light, is 299 or 3. Okay. This is the uh, the scaling factor. And you can see that now it turns to be 1, almost 1, approximately 1 times 10 to the 13 meters. So that's possible to detect right now. 11 meter here is also possible to detect the wavelength in this region. When you go further beyond the postulation by the Broglie, is there any development about this theory? The Broglie just proposed this idea. You know, he was just a guy who wrote his PhD thesis, doctoral thesis. It can be true or it can be false. No one knows. Okay, 3 years goes by. In 1927, two scientists, Davidson and Gamma, at Bell Telephone Laboratory. You know, in my field, in telecommunications, this laboratory would be the one. It would be the greatest laboratory in the world, okay, in the United States. But I don't understand why these two guys studied something about physics also. But this laboratory is dedicated to telecommunication, okay, like in my field. You know, the most famous theory of telecommunication was created also from this laboratory. Sorry, อะไรครับ Korea อยู่ใน United States ครับ อันนี้อยู่ที่ US ครับ อยู่อเมริกา Well, the name itself is taken from Alexander Graham Bell, you know, Bell. And the theory, which is still the art of the stage, was created from this laboratory. And that guy is Cloud Channel, you know, Cloud Channel. You know, he developed information theory. Cloud Channel worked also in this laboratory, but he is not from engineering. He studied mathematics. Okay. The next one is Davidson and Gamma. Discover the electron diffraction. Okay, that's very close to the idea by the Broglie, because the Broglie believes that electron behaves also as wave, and that's why we have wavelength. This result can somehow confirm the idea of the Broglie. Okay, the Broglie just created the theory. And let's move to Germany. Two guys, Esteban and Stan, okay, demonstrated that the alpha particle has also diffraction. So it would be in the same way, right? Because this is the diffraction of the electron, this is the diffraction of alpha particle. Alpha particle is bigger than electron, right? So these two results could confirm the truth, the validity of the Broglie theory. Okay, more experiments. I'll leave you. You know, if these two results didn't exist in the past, I think that no one is going to believe the theory of the Broglie, right? Which is very far from the classical theory. We would believe that electron is only particle, but we have also the wave idea for many particles. And more experiments were discovered. And those discovered the diffraction of low energy neutron and large molecules. All these discovery gives a strong support to the double rays hypothesis. And after that, Werner Heisenberg found an I think not this one, right? Werner Heisenberg found an equality for the product of the uncertain coordinate x, delta x, and the corresponding uncertain momentum delta t. So the product of delta x and delta p should be always greater than or equal to h by 4 pi. Or if you want an expression in terms of reduced time constant, it's h slash, which is h is s slash is h by 2 pi. And it means that the integral, neither the momentum nor the position of the particle can be measured simultaneously with arbitrarily great precision, as classical physics would predict. Let's try to use the Werner Heisenberg formula. Delta x delta p greater than 1 by 2 h slash, right, or h by 4 pi. Well, let's consider an electron that has that is confined in a box that has the shape of cubic. Well, just each side of this box is only one angstrom, 10 to negative 10. So the size of the box, is like this. Okay, this is 1 meter, 1 meter. And also here, 1 meter. All right, and electron just stays inside this box. So let's compute the minimum speed. The bugging up cái ai biết được. Okay. ดีขึ้นเลยนะ as an electron just stay inside this box, and what is the minimum uncertainty? So delta x min. What is that, right? What is the kinetic energy of the electron with the above momentum? Okay. Then one also find second quantity, that's the kinetic energy K of electron. What is that? Of course, you have delta x and delta p, right? Greater than 1 by 2 H slash, which is the reduced version of the typical Planck constant. You know, H slash is H by 2 pi. H slash is H by 2 pi actually. The reduced Planck constant. Or H bar, you can say H bar. H by 2 pi, right? When you want to know delta momentum, right? Not delta x means delta p means delta p minimum or delta px, okay. If delta x delta p divided greater than this, so when you move delta x to this one to the right hand side, it's going to be delta p greater than h by 4 pi, and the lower one will be delta x. Delta x is the size that electron can move, so it's 1 meter. So delta p will be h, which is 6.6 times 10, approximately 10 to negative 34, divided by 4 pi, and distance is not 1 meter, sorry, it's 10 to, sorry, stupid, 10 to negative 10. Okay, 1 angstrom, sorry. 1 angstrom. So you need to substitute here as by 10 meter and compute it. The minimum value of the momentum, that's the 5.27 10 to 25. Okay. 5.27 times 10 to negative 25. Of course, the momentum is the product between the mass and the speed, right? So the unit would be kilogram and meter per second, right? Okay, I hope you can. You would be able to compute it. The next thing is kinetic energy. EK or K, simply K, kinetic energy. The minimum value will be, you know that P is equal to mv, right? We're going to transform mv to 1 by 2 mv squared, right? In order to get that, of course, you have K is 1 by 2 mv squared, right? If you move V to the right hand side, you separate it. It's going to be 1 by 2 mv and V, right? Like right here. So, no, we cannot do that. Another possibility is that you need to add M to be here, right? So that it's going to be another momentum term. Okay, if you move M to be here, and you need to multiply by M. But because these will cancel each other. You will get 1 by 2 mv square divided by M, right? And of course, mv is actually momentum. You get 1 by 2 p square by m, right? P square by m. P P, which is the momentum, which is delta momentum that we have got before, which is 5.27 right here. So it's time to compute it. Right. K, the kinetic energy will be 1/2. And momentum, which is what we have got before, 5.27 times 10 to negative 25. But this has to be with the power of 2, right? Because P has the power of 2 here. The next one is the mass of that particle. What is that? It's electron, right? The basic value of electron mass is 911, 10 to negative 31. Right. Then you get the approximate value of the kinetic energy, okay, which is 0. First of all, you get the kinetic energy in terms of joule, which is 1.5 times 10 to negative 19 joule, right? But this value is not appropriate to us. We are considering the tiny scale, tiny particle. We need to change the scale of the energy. One of the ways that we're gonna divide by the sharp value of the electron is 1.602, 10 to negative 19. That's electron volt. Joule per electron volt. So you're gonna get 0.95. Unit of this is electron volt. Okay. That's the way to compute the minimum kinetic energy. Minimum because the lower speed of the lowest value of the momentum is right here. So this is only the minimum kinetic energy. Okay. Now let's move to the bigger thing. ได้ไหมครับขอลบนะครับโอเคผมก็ว่าแล้วเก้าอี้ผมหายไปไหนคนนี้เอาไปนี่เองไม่เป็นไรนั่งได้สบายๆ Great. Now we will consider the next one which uses different concept. Okay, different concept. Speed of electron is measured to be this value 5 times 10 to 3. 5 kilometer. Okay. โอ้เร็วไหมอิเล็กตรอน1 วินาทีวิ่งไป 5 กิโลเมตรโอ้เร็วนะ to an accuracy of 0.0 โอ้โหไปก่อน 0.003%. What is the meaning for that? So relative. This is ถ้าใช่ป่ะก็มันจะเป็นอะไรแปลเป็นค่าตัวแปรอะไรได้เลย 0.003 ผมก็ทำเจอโจทย์นี้ปีนึงผมก็ลืมนะเวลาใช้ทำ It's going to be delta x also. Find the minimum uncertainty in determining the position of the electron. So they are talking about delta x min, right? Delta x min. I think it's delta p min. Delta x min. This is the speed and the accuracy. Position. Which concept should you? ผมลบตรงไหนได้บ้างไงอันนี้ลบได้ไหมเนี่ยอันนี้นะอันเก่าเดี๋ยวมันปิดหน้าจอแล้วมันมองไม่เห็นจอในสกรีนครับฝั่งนี้ก็ต้องฝั่งนี้ดีกว่าเอาฝั่งไหนครับฝั่งนี้นะโอ้คุณสาววาดหมาเหมือนมาอย่างดีผมมาวันไหนตัวการ์ตูนมันก็ยังค้างอยู่เลยแสดงว่าอาจารย์เขาไม่ได้เขียนเลยใช่ไหมเนี่ยโอ้คุณใช้คำพูดอย่างนี้กันเลยเหรอเนี่ยโอ้โหanyway remove Okay, because they say something about v, right? Velocity uncertainty. So it means they are talking about delta v. Okay, delta v is the accuracy of something like this. So you're gonna have 0.003% okay, of the speed, which is v. Okay, so this is what you can infer from these text, right? 0.003% from the speed. But is there any relation to our target, which is what we have just learned? It's Werner Heisenberg, right? Werner Heisenberg answer is going to be delta p and delta x is greater than equal to x by 4 pi. Delta x delta p greater than by 4 pi, right? The Werner Heisenberg inequality right here. But what they would like to know the minimum determining the position of electron. So the distance would be the you need to move delta p to the right hand side. So delta x greater than h by 4 pi and delta p, which is the momentum, right? So the minimum would be this side, right? This is minimum. The minimum value, you cannot be less than this, right? You cannot be less than this. The accuracy of the position of the electron. You cannot be lower than this is the minimum value. So delta x mean will be h by 4 pi and p. Oh, sorry, delta p. Delta p, right? But in order to calculate this quantity, of course anyone know the Planck constant, right? Is 6.6, 2, 6, 10, 2, negative 34. 4 pi is quite simple, right? 4 and pi. But delta p, what is that? Yeah. You know, P is mv, right? P is mv. The mass is constant. When you have the uncertainty of the velocity, it means you get also the uncertainty for the momentum. So delta P will be m delta V. You just substitute this one to this location. Okay, you're gonna get h by 4 pi m delta V. Okay, nothing will be difficult. 10 to the negative 34 divided by 4 pi. Mass of what? Mass of this particle electron 911. Okay, 911 10 to the negative 31 and delta V. Delta V would be, what is that? 10 to, it's actually 0.003 by 100 of the speed of the electron. 5 kilometer, 5 times 10 to 3, right? That will be 15 by 100. Or simply speaking, it's 0.15, right? We're gonna have here 0.15. Leave it in the calculator, or you can calculate by hand. I'm not sure. You're gonna get direct 0.385. 0.386. Okay. Meter. Oh, millimeter. Sorry. Millimeter. Millimeter. Okay, which is very small, right? Uncertainty in 1 millimeter is acceptable, but only 0.4, 0.3 is even smaller than 1 millimeter. ฮะ อันนี้อยู่กลางภาคไหม ใช่ครับ ยังไม่ได้นั่นกันแล้วไม่ใช่หรอ ยังไม่ได้ มันจะเป็นพวกอะไรอะนิวเคลียร์ฟิสิกส์ป่ะที่มันจะอยู่ปลายภาค เราน่าจะจบอันเนี้ยบทเนี้ยจนถึงสอบกลางภาคครับอย่าลืมว่าเราหายไป4คาบนะครับ ตอนที่ฟุตบอลจตุรมิตรคุณอะที่คุณไปเด็ดกุหลาบแล้วก็อะไรอย่างนั้นหายไป4คาบ จริงบทนี้มันควรจะต้องจบด้วยนะเนี่ยถึงตรงนี้แล้วอะมันก็4คาบน่าจะหมด แต่ว่าหายไปนะครับ Okay, that's the Werner-Heisenberg uncertainty principle. Okay, you now has already got the taste of this idea. But there is another form of the Werner-Heisenberg when someone derives it in terms of energy and time. Okay, energy and time. Okay, instead of momentum and x displacement. Okay, the constant is the same, which is h by 4 pi 1 by 2 h slash. Okay, now it's energy and time. This formula is valid for any particle, even bigger one, like sodium atom, Na, right? Na sodium. Na sodium. you know the technology for building or making the battery now would shift to sodium, okay, instead of lithium. Lithium is more and more difficult to find on the earth, and so on. We are going to move to sodium. So sodium is power. Sodium stay in a resonant state. With the average time 1.6 10 to -8, and then return to its ground state. Find the uncertainty. So it moved from one shell from the first excited state to the ground state all the time. Okay, it's called resonant. With the average time 1.60 10 to -8 seconds. So it's 16 nanosecond, right? Find the uncertainty in energy at the resonant level. So it's delta E, right, in this case. Delta E and delta T greater than h by 4 pi, right? Delta E, delta T greater than or equal to h by 4 pi. That's another version, another form of Werner-Heisenberg uncertainty. Because our target is the uncertainty in energy, so delta E would be kept on the left-hand side. We're going to move delta T to the right-hand side. Delta E is greater than h by 4 pi. And delta T, right? So it's going to be 6 10 to -34 and 4 pi. What is delta T? Delta T is right here. Resonance. It moved from this one, okay, to the first excited state to the lower, the ground state. 1.6. Time sent to -8 seconds. So you use the calculator again, and it turns to be 3.29 6 10 to -2 Joule. And now you can convert it to the EV, right, electron volt easily. You just divide by the 1.602, right? เดี๋ยวผมงงว่ามาได้ไง329แล้วมา659มันต้องเบอร์แน่นอนเลยเนี่ยมันต้องผิดแน่นอนมันต้องเลขเดิมใช่ป่ะจับมาหารใช่ป่ะเฮ้ยผมว่าเลขนี้เลขผิดเนี่ยเพราะ 3.2 หาร 1.6 มันจะต้องได้2นิดๆใช่ป่ะเลขนี้เลขผิดเดี๋ยวผมไปแก้ให้เกิดอาการเบลอได้นะตัวเลขนะเลขนี้ไม่น่าใช่นะ 1.6 หาร 6 มันไม่ได้2แน่นอนใช่ป่ะมันต้องได้แถว4ป่ะ4หรืออะไร3กว่าเกือบ4อ่ะไม่ใช่เรื่อง 6.5 ไม่ใช่อันนี้เกิดอาการเบลอผมไปก๊อปอะไรมาแล้วอันนี้ไม่ใช่นะเดี๋ยวผมแก้ให้นะ It should be 3.29 369 โอเคต้องเป็นเลขเดิมนะ แค่จับมาหารกับ 1.6 เฉยๆนะครับอย่างนี้โอ้ขอโทษมองไม่เห็นโอเค this one it should be so and then you will get 2.05 10 to negative 8 eV okay electron volt that's the minimum energy uncertainty okay the reason why we say it's minimum because you cannot be lower than this one. This is the minimum value. So that's why they say minimum of the energy. Alright เกิดอาการเบลอเฉยเลยเลขอาจจะก๊อปมาจากที่อื่นมั้งแล้วก็ไม่ได้เปลี่ยนเลขครับ 6.59 เลขเก่าปะใช่ปะน่าจะจากข้อก่อนหน้านี้ปะไม่ใช่นะไม่รู้มาอย่างไรครับ 6.59 แล้วแต่มันผิดนะครับเดี๋ยวแก้ให้นะครับ ทั้งในสไลด์และในหนังสือนะครับ Okay now we move to there is conflict okay because in I have ever แบตเหลือ 10% แล้วเดี๋ยวเจ๊งนะครับเดี๋ยวทำไงดีหัวปลั๊กอีกอันนึงไม่ได้เอามาด้วยครับเดี๋ยวเสร็จนะครับได้เดี๋ยว10แล้วมาก็ต้องเอาปลั๊กยางมา2 อันแล้วนะครับผมประมาทเอามาอันเดียวทีแรกคิดว่าจะไปรอชาร์จที่ห้องนู้นนะครับไม่ทันละแบตลงมาเยอะนะครับเพราะว่ามีสอนเมื่อเช้านี้ด้วยนะครับแบตก็เลยนะครับก็อาจจะถูกใช้มาเยอะanyway ถึงไหมขอลากสักจากใครสักคนหนึ่งนะครับโอเคขออนุญาตลากจากของคุณหน่อยนะแบตของผมเหลือ10แล้วนะครับเดี๋ยวสอนต่อไม่ได้นะครับได้ไหมครับเสียบทางไหนเลยนี่ได้ไหมวันนั้นครับก็มาพักไปตรงนี้ก่อนถึงไหมครับน่าจะถึงอยู่นะสายยาวไว้ก่อนดีกว่าสั้นนะครับโอเคเข้าไหมครับเข้าแล้วโอเค alright yeah I have used the wrong formula which is taken from book number 2 okay you don't need to worry about it it was h by 2 pi but forget or don't use that forget about it now we move to the quantum mechanics which talks about how we describe the electron orbit you got the idea how to compute the energy level right for several orbits of the electron. Now we're going to talk how to arrange the electrons onto solar orbits. And we need to know the name of the name of each orbit, which was assigned by physicists. And we're going to talk about orbital quantum. Orbital momentum as well. Okay, In the Bohr theory, the allowed energy depends only on the principal quantum number n. Okay. You know n, right? When you have En is, if you can remember the formula, En is negative 13.6, right, by n squared, right? Okay. N is the principal quantum number. But we have something more than that. Okay, actually, there are two more quantum numbers, which is called L and ML. Okay, L is called orbital quantum number. All these two additional quantum numbers are derived from the Schrodinger's wave equation. So it's too difficult for us in the high school level to get into the detail of the Schrodinger's wave equation because it's a combination of complex number and differential equation. If you want to see what is Schrödinger wave equation, okay, so you understand why you are not ready to talk about the Schrödinger's wave equation. In German, equations would be called Gleichung. Okay, Gleichung. Gleichung means equation in English. Okay. Lösen means to delete. Okay. Of course, it's a mix, a combination of complex number, differential equation. Okay, I is square root of minus 1. H slash is what you just learned. Okay, H slash is h bar, h by 2 pi. This is the psi, which is the function that depends on the x location of the electron position. It depends on x, y, z, and time. Okay, but you know this symbol, right? Which is partial, right? Curve. Curve is the derivative with respect to only time. I would say. I can teach, but not in the high school level. Okay. Okay. Psi depends on x, y, z, and time. It depends on 4 variables, but this derivative is made with respect to only time, the last one. Okay. So, and then this one is the partial derivative with respect to x. The second order partial derivative. Okay. When you are more mature, when you are at the bachelor degree or master degree, you will be able to solve this one. Okay. And then you will find that there is orbital quantum number right here. Okay, but I cannot show you in the high school level how to get L and ML. Okay, we skip it. Okay. We have two additional quantum numbers that could be found from the Schrodinger's wave equation. เท่าที่ผมศึกษานะครับ Schrödinger นี้เป็นนักฟิสิกส์ที่แบบยอมไปอยู่กับพวกนาซีเยอรมันยอมไปเป็นลูกน้องฮิตเลอร์นะครับ
Schrödinger เป็นหัวหน้าโครงการอะตอมิกบอม
อันนั้นแหละนั่นแหละ
แต่ว่ามันเฟลเพราะว่าโดนพวกนอร์เวย์ขโมยน้ำมันหนักเลย
ประมาณนั้นนะรู้สึกไปยอมไปเป็นลูกน้องของพวกฮิตเลอร์นะครับคนนี้นะเชอริงเกอร์นี่นะก็ว่ากันไปไม่เป็นไรเราไม่เกี่ยวกับการเมืองนะเพราะเราทฤษฎีอย่างเดียวนะครับโอเคanother one which is called magnetic quantum numbers this is ML So totally at the moment, we have 3 quantum numbers: principal quantum number N, orbital quantum number L, orbital magnetic. Okay, we have magnetic quantum number ML. You will see the detail how to express N and LML later. The allowed values for these quantum numbers are given by, of course, N from what we have learned before. N should start from 1, right? N cannot start from 0. If this one is 0, energy will be infinity. Will be infinite. N cannot be 0. Sorry. N cannot be a decimal number. เดี๋ยวขอจิบยาแก้ไอสักนิดนึงครับ โดนแอร์คุณแล้วคันคอนะครับ ผมไม่เป็นไรครับ ไม่ต้องปิดแอร์ครับ เดี๋ยวคุณร้อนครับ โอเคครับ แจ๋วมากครับ Okay. N is an integer that can start from 1, 2, 3, 4, 5, 6, 7. You cannot say 2.7, no. Only 2 or 3. Okay. So it's a member of the integers natural number, right? 1 until infinity. And if you substitute N as infinity, it's going to be 0, right? This one. Oh, yeah, because this one, the numerator, the denominator is infinity, this ratio will be 0. L would be a member of the set with 0, 1 until n minus 1. Okay. For example, if your n ผมเขียนยังไงได้ If your n is 3, L would be 0, 1, 2 only. Okay. 0, 1, 2. If your n is 3. And ML. ML will start from the negative value of that L until a positive value of that L. So it's 2L plus 1, I think. 2L plus 1. So the allocation could be for number 3, right? Number 3, you would have ตรงไหนได้ตรงนี้แล้วกันนะขอลบอันเก่านี่นะครับ When your n is 3, the first n you can have is n equal to 1, right? And L could be only 0, right? Because 1 minus 1 will be 0, and there is no other possible value. And ML would start from minus L to plus L. Because L is 0, ML will be 0. That's the fourth possibility. When n is 2, your L could be 0 and 1, because 2 minus 1 will be 1, so it could be 0 and L is 1. Okay. But for L is equal to 0, you're going to have ML equal to 0. But for L equal to 1, you're going to have ML such as minus 1 ml 0 ml equal to 1. Okay. According to this possibility, okay, this set, and if your n is equal to 3, okay, if your n is equal to 3, your L will be L equal to 0, L equal to 1, and L equal to 2. There are 3 cases, 0, 1, 2. Of course, 0 would bring you to only ml equal to 0. L equal to 1 will be the same like this. You can have ml equal to minus 1, ml equal to 0, ml equal to plus 1. And regarding L equal to 2, what is the possible value of ml? Of course, you need to start from the negative value of L, which is 2. So ml will be minus 2, ml will be minus 1, ml will be 0, ml will be 1, and the last one, ml is number 2, plus 2. Okay. In this case, you would have single possibility. This is 1. Okay. And here you have 1, 2, 3, 4. So in this case, you have 4 orbits. And in this case, n equals 3, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. You have 9 possibility. That's 9. Okay, this is how we arrange. But actually, it's not the final. We still have one more quantum number. Okay, we still have one additional quantum. One may notice that the number of allowed state for n is infinite. Okay, infinite. Number of allowed state for L is n. Going to start from 0 until n minus 1. When you count it, it's going to be equal to n. Number of allowed state for ml is 2l plus 1. Yeah, the way to generate is as I explained it on that whiteboard, on the left whiteboard. If your n is 1, you can have L equal to 0, ml is 0. If your n is 2, you will have L equal to 0 or 1. And for the case of L equal to 0, you have only one possibility, that's L equal to 0. If your L is 1, you can have 3 possibilities, minus 1, 0, 1. So totally you would have 4 allowed states for the case of n equal to 2. N equal to 3, of course your L could be 0, 1, 2. And of course, if you start from L equal to 0, ml is 0. You just copy this one to the first 2 lines. And in the last line, you can start from, because L equal to 2, right, you can start from minus 2, minus 1, 0, 1, 2. These are 5 additional states. Combined with the previous 4 states, allowed states, you're going to get 9 allowed states. N equal to 4, of course, it's going to be 0, 1, 2, 3. หมดเวลาขอโทษครับไปแล้วครับผมไม่ได้ยินเลยเสียงขอบคุณมากครับ See you on Friday เรื่องนึงคือคนที่ควิส ที่ผมพิมพ์มาในไลน์นะคนที่ควิสแล้วไม่ผ่านหรือสุภารัตน์คุณได้0เนี่ยคุณต้องเอาใจใส่เขาบอกว่าให้แก้ได้นะจนถึงสอบซ่อมให้ได้ทำอะไรซ่อมให้ได้นะให้มันถึงครึ่งหนึ่งนะครับ คนอื่นด้วยมั้งแต่ห้องเนี้ยได้เยอะห้อง5เดือดร้อนห้องนี้ไม่ค่อยเดือดร้อนห้องนี้มัน4เกือบ5แล้วนะครับไม่แต่ถ้าคนไหนตกนะครับก็หาเรื่องแก้นะก็คือเลือกเอาครับว่าจะเอาแบบใดนะครับ คุณจะเอาแบบใดดังที่ผมพิมพ์ในไลน์แล้วก็แจ้งผมมานะครับระยะเวลาให้ก็คือ3 อาทิตย์โอเคไหมคุณจะเสนอก็ได้คุณจะทำเป็น YouTube ก็ได้คุณจะทำเป็นรายงานก็ได้เอาที่คุณโปรดปรานหรือคุณจะทำเป็น PowerPoint อย่างเดียวก็ได้แล้วมันนำเสนอต่อหน้าห้องให้เพื่อนดูครับก็เลือกเอาคุณจะเอากลุ่มเดียวได้แต่ไม่ใช่เลยว่าตกทั้งหมดเราทำชิ้นเดียวฮะ
แล้วซ่อมก็แค่
เราทำอันเนี้ยพรีเซนต์ได้10เลยได้ครึ่งของ10ก็คือ5ฮะเกี่ยวกับนักฟิสิกส์ที่คุณชอบสักเลือกมาสักคนนึงโอเคไหมเอาวันนั้นโอเค I have to go see you on Friday bye bye ครับสวัสดีฝากสลับกล้องไว้นู่นหน่อยนะครับอ๋อได้คุณจับสมุดได้ว่างเอาวางเลยผมเขียนไม่ค่อยถนัดโอเคครับขอบคุณครับลืมอะไรไม่ลืมนะเชิญครับสวัสดีครับอยากฟังค้าข่าวดีด้วยเดาเลยเล่นเครื่องดนตรีไทยเดาเลยยอดเยี่ยมครับ
เขาที่พูดมันเร็ว
เร็วครับเร็ว
มากผมยังต้องเพิ่มสปีดครับ
อันนี้คือมันหกใช่ป่ะคุณไม่ได้อ้วกใช่ป่ะหรือว่าอันนี้มันหกใช่ป่ะไม่ได้อ้วกคุณใส่มานะTest 1, 2, 3.ลืมประกาศในห้องนู้นด้วยนะครับ วิชา IS นะ วิชา IS คุณเนื่องจากผมเพิ่งทราบว่าคุณทำกัน2 ห้องเชื่อมกัน2 ห้องแล้วเวลาคุณส่งข้อมูลอย่างของห้อง5เขาดูไม่ได้เพราะเขาไม่ได้อยู่กลุ่มเรา SCI ของเราให้คุณสร้างกลุ่มไลน์วิชา IS โดยเชื่อมทั้ง2 ห้องนะเอาเพื่อนทั้ง2 ห้องเข้ามาอยู่ในกลุ่มไลน์โอเคปะโอเคได้ไหมครับเนี่ยที่เราทำเนี่ยมันเป็น SCI เฉพาะ 604 หรือว่า 605 อย่างเงี้ยเพื่อนอีกห้องเขาดูไม่ได้นะว่าคนไหนพิมพ์ชื่อมาแล้วดังนั้น
พอดีเช็คให้ผมไปหาหมอ
เดี๋ยวแป๊บนึงนะเดี๋ยวขอโหลดแป๊บนึงเดี๋ยวคุณเดี๋ยวเลขที่อะไรคุณจดมาร์กไว้เขียนไว้บนคุณชื่อเลย605 right หมายเลขไหนครับคนไหนหมายเลขตรงไหนเนี่ย
ไม่มีมาร์คเกอร์จ้
ะนี่ชื่ออะไรครับ
ผมห้อง4อาจารย์
ไปแล้วเหรอ
เซม
หมดเวลาของคุณไปแล้วนะ
เดี๋ยวช่วยได้ไหมอาจารย์ครับเดียวผม
กมลสิทธิ์เนี่ยนะครับ
ผม
เขาแจ้งว่าป่วยไม่ใช่เหรอ
ป่วยแต่ว่าผมอยากมาไงพอดี
คุณ
นอนแล้วก็กินยาแล้ว
หายก็ได้
ผมไม่อยากขาดจานบ่อย
มันไม่ใช่ผมบ่อยหรอกเดี๋ยวดร.โชคเขาจะเล่นคุณดิ
ก็ผมไม่นี่ไงผมไม่อยากขาดบ่อย
นี่
ขอบคุณครับ
ครับผมนึกว่าห้องคุณหรอกโอ้โหมันหลงเปิดไฟล์รีบเลยเดี๋ยวชี้แจงก่อนเรื่องกลุ่มไลน์นะเนื่องจากการกระจายข่าวมันไม่ครอบคลุมนะครับขอให้พวกคุณนะครับทั้ง604และ605นะครับเปิดกลุ่มไลน์กลุ่มใหม่นะแล้วผมจะเขียนเองว่าเป็นวิชา IS 604 605นะวิชา IS นะครับเพราะว่าเพื่อนเขาไม่เห็นอันเนี้ยที่คุณพิมพ์มาเนี่ยเพื่อนอีกห้องเขาไม่เห็นแล้วเขาก็ไม่รู้ว่าสรุปกลุ่มเขาได้พิมพ์ชื่อมาแล้วโปรเจกต์มาแล้วหรือยังไทเทลอะไรเมมเบอร์อะไรเขาไม่เห็นนะครับดังนั้นแล้วตอนถึงห้องนู้นสุดท้ายผมรวม มันไม่ถึง58 คน บวกได้ประมาณ47 คนหายไป11 คนเอา11 คนจะไม่เอาคะแนนใช่ป่ะหรือว่ายังไงนะครับให้คนกลุ่มไหนก็ได้นะตั้งกลุ่มไลน์ขึ้นมานะครับแล้วก็เชิญเพื่อนทั้ง2 ห้องนะครับทำคล้ายๆกันอย่างเงี้ยเราจะคุยกันเรื่อง IS ที่แรกผมก็คิดว่าจะใช้กลุ่มไลน์เดิมของฟิสิกส์แต่ปรากฏว่าคุณทำข้ามห้องคุณทำระหว่าง2 ห้องมันก็สื่อสารกันยากแล้วทีนี้ครับเพื่อให้มันง่ายนะครับให้คุณเปิดกลุ่มไลน์ด่วนที่สุดเลยนะแล้วก็เอาชื่อผมเข้าไปด้วยนะจะได้จัดการแจ้งคะแนนอะไรคุณได้ง่ายๆนะครับโอเคOkay, let's talk about เอาเดี๋ยวธุระ ธุระเห็นตัวธนากรไม่ได้ก่อนธนากรเอามาของคุณจัดการยังไงมันขาดเหลืออะไรครับเดี๋ยวกลับบ้านแล้วมันคุยกันไม่รู้เรื่องมันอยู่ไกลกันครับ
หรือรอหลังเลิกเรียนก็ไม่น่านานหรือรอหลังจากสอบเสร็จก็ได้
ไม่เป็นไรเอาตรงเนี้ยเดี๋ยวผมเก็บของอีกเสียเวลานานกดปุ่มไปให้เขาเฉยๆใช่ไหมครับ
แล้วมีอาจารย์ล็อกอินไปแล้วใช่ไหม
ใช่ไม่อยากค้างคาครับเนี่ยผมเข้าให้คุณละจะกลับแล้วเหรอโอ้โหมีรีเควสหลายอย่างยังเดี๋ยวรอขอแป๊บนึง
ได้
แม่บวชชยากรเดนิสใช่ป่ะเคยติ๊กแล้วธนากรกลับมาธนากรยังเดี๋ยวเอาธุระคนนี้ก่อนแบบว่าเดี๋ยวผมกลับบ้านแล้วมันคุยยากไม่เห็นตัวกันนะครับถอดก่อนเดี๋ยวคุณเห็นภาพผมเดี๋ยวคุณเข้ามาแก้คะแนนปริญญาตรีอะไรผมเอาเดี๋ยวมันยาวไม่ไปไปละต้องไหนต่อ
เมื่อวานเมื่อเช้าผมไปช่วยดร.โชคมาด้วยอะไรเยอะแต่
มันซับซ้อนอันเนี้ย
ได้ก็ไม่มีอะไรน่าจะแค่เดี๋ยวผมขอเช็ค
นี่ไงผมเขียนให้คุณหมดแล้วไงแล้วมันขาดอะไรอีกนี่ไฟล์ผมอัพโหลดให้แล้ว
เดี๋ยวงั้น
นี่ไงรีวิวซับมิทผมก็กดให้แล้วเมื่อคืนเนี่ย
มันขาดอันนี้ครับเนี่ยเพราะว่าใช่
เอาอะไรจากผม
เดี๋ยวเช็คก่อนมีแค่นี้นะครับที่ต้องกรอกคือถ้าเกิดว่ามันเกาะเนี่ยแบบนี้คือมันได้แล้วครับ
ก็ผมก็ติ๊กเมื่อคืนนี้ไงแล้วคุณบอกว่าไม่ได้ยังไงเมื่อคืนผมก็ขีดถูกอย่างนี้แหละ
คอลเลจชุดอัพครับ
อ๋อ
มันต้องหามหาลัยที่จานหาเจอว่าเพราะบางอันมันแบบมหาลัยมันหาไม่เจอต้องไปแอดเอา
อย่างเงี้ยเลยนะอย่างเงี้ยไม่มีหรอแล้วทำไง
อะไรไม่ที่ผมของอาจารย์ทำมาถ้าไม่เจอก็เดี๋ยวมัน
ทำไง
โอ้ my god
S เลื่อนมา S เลื่อนมา
มันบางอันมันจะแบบไม่มีเลยมันถ้าเกิดแบบว่าพี่เราให้หาจากของจานอยู่เมืองไหน
นครนายก
แบบนี้น่าจะไม่มีต้องไปเนี่ยคือมัน มันให้แอดเข้าไปเองครับ
เดี๋ยวเมืองเขียนผิดเดี๋ยวเอาแบงคอกก่อนเลย
เหมือนมันมีแค่บางมหาลัยที่มันไซน์อัพมันถึงจะขึ้นนะแบบจุฬาอะไรพวกนี้ขึ้นธรรมศาสตร์
อันนี้ไม่ขึ้นแล้วคุณทำไง
ก็ของสวนกุหลาบก็เวลาผมทำให้ดร.สวนก็ไม่ขึ้นแล้วก็ให้กรอกจากแบบนี้เองครับ
เอ้าผมไม่ได้อยู่อเมริกานะ
เขาเปลี่ยนประเทศได้
ครับไทยนะทีพิมพ์ทีไม่ได้เหรอ
ไม่ได้
พิมพ์ทีไทยแลนด์อย่างเงี้ยนี่
นั่นแหละ
ก็พิมพ์ไปเลยนะครับ
ใช่
ตรงนี้นะครับเรียบร้อยไหมเอ้าตายแล้ว
เดี๋ยวลองเหมือนมันต้องมี address อะไรขึ้นเลยใช่ลองคิดให้มันขึ้นมา
แบงคอก
เอ๊ะ
อืม
จุฬาไม่มีจานมีเมื่อกี้มันมีเมื่อกี้ยังขึ้นอยู่เลยอันมันแค่จะไปที่ตรงนี้เช็คชื่อหน่อยได้ไหมครับ
ฮะเอ้าคุณอยู่ห้องนู้นไม่ใช่เหรอ เกี่ยวอะไรกับห้องนี้ของคุณ
ถ่ายรูปว่าไง
ฮะ
ให้เพื่อนถ่ายรูปผมก่อนได้
ถ่ายรูปมันเกี่ยวอะไรยังไงเดี๋ยวสีนะ
ห้องนี้นะ
คาลินนี่โรดแล้วไงอ่ะ
อันนี้คือ address อาจารย์แบบรู้จัก address คร่าวๆครับ
อันนี้ก็ได้
ปากกับเยี่ยมไม่ถูกแล้วไม่สามสิขวาสั่งไม่เด็ดบ้าน
ก็ได้
มาเลย
แล้วก็
เรียบร้อยหรือยัง
ได้แล้ว
เสร็จแล้วนะ
เดี๋ยวต้องกดถ้าได้แบบเรียบร้อยทุกอย่างก็สับมิทแล้วก็เรียบร้อยวันนี้ถือว่าได้แล้วเดี๋ยวอาจจะลองอ่านดูก่อนมันแค่อันนี้แค่เหมือนคอนเฟิร์มเฉยๆว่าแบบ
ก็จะเอาเสร็จเลยเหรอทำไงอ่ะ
อันนี้ก็เสร็จเลยครับ
พิมพ์ชื่อผมนะ
ชื่อแล้วก็เดี๋ยวก็ติ๊กถูกอันนั้นก็เรียบร้อยแล้ว
ครับ แล้วก็เดทวันนี้นะครับ
ใช่แล้วก็อันนี้ติ๊กไปก่อน
ติ๊กหมดอ่ะ
การลองอ่านก่อนก็ได้ครับแต่มันไม่มีอะไรมาก
โอ้ผมไม่น่าทำอะไรผมหรอก
ครับ
โอเคครับ
อันนี้ก็ได้แล้วครับ
เรียบร้อยนะ
ขอบคุณครับ
โอเคครับ
ไม่ถูกแล้ว
Okay, now let's consider our class attendance. คณาวุฒิครับคณาวุฒิแล้วก็ชัยากรครับ แล้วก็พันวินครับพันวินฮัลโหลอยู่ไหนพันวินนัทวัฒน์ครับ
ไม่ใช่
ธนากรพัฒน์ศิลภพอยู่ไหนโอเคครับอันนี้วัดครับโลดระวีอยู่ไหนเนี่ยโลดระวีมองไม่เห็นครับสหรัฐครับโอเคครับสมัตอยู่ไหนเลยจีโน่ครับอ๋ออยู่นี่แล้วก็แดนฟ้าไปไหนแล้ว ก็ปุญญวีนะครับปุญญวีภูมินันท์กันเอกกฤษเคครับกฤษเคณัฐนนท์ไปแซบทักกฤษครับทักกฤษปาดธรรมครับกฤษจีครับกฤษจีธนทรณฤทธิ์กสิเดชครับ พัฒดลเมื่อกี้พัฒดลมาแถวๆนี้ไม่ใช่ไปไหนแล้วพัฒดลไปไหนนะไปแล้วภูเมศนะภูเมศวิบูลย์ลานะวิบูลย์ลาตั้งไป เฮ้ยไม่ใช่ดิผมจะต้องติดต่อ
ไม่หยุด
Oh, the export here. That's the. Oh, what is that? 2M M605 นะครับอย่าลืมนะครับคุณตั้งศิรวิทย์แล้วคุณไปไหนมา
อยู่ห้องนี้
ศิรวิทย์เอ้า604 ก็เดี๋ยวผมขอไปล้างแว่นนิดนึงครับเนื่องจากว่ามันมัวมากครับ
เ
ครับ
พวกมึงจะไปพัดหรือว่าทำไมวะ
แล้วยอดทุนนิยมมันเป็นระบบที่ดีไหม
นิยมแล้วแต่ว่ามันก็มีข้อดีข้อเสียด้วย
แล้วคิดว่าข้อดีกับข้อเสียอะไรบ้าง
ถ้ามันมีการแข่งขันที่อย่างยุติธรรมเสียงผมไม่ไหว เดี๋ยวเปิดไมค์แป๊บนึงถ้าเสียงถ้ามีการแข่งขันอย่างถูกต้อง มันก็จะทำให้เกิดการแข่งขันทำให้เกิดคุณภาพของคุณภาพที่ดีราคาที่ต่ำแต่ถ้ามันไม่ได้แข่งขันจริงๆมันก็จะหัวแล้วทีนี้ประชาชนคนบริโภคครับมันก็จะได้ของที่ไม่ดีราคาที่แพงยกตัวอย่างเช่นซิมการ์ดอย่างเงี้ยซิมการ์ดที่คุณใช้อินเทอร์เน็ตบริษัทใหญ่รวมกันอันของที่มันดีๆอินเทอร์เน็ตวิ่งดีๆราคาถูกๆมันก็ไม่เหลือให้คุณละเพราะว่าฉันตั้งใจที่จะขายแพงๆแล้วก็จ่ายเน็ตห่วยๆอย่างเงี้ยมีเจ้าเดียวคุณก็ต้องซื้อผมพอเข้าใจไหมครับพอเข้าใจไหม
เรื่องหมออยู่ไปเลยขอตัวครับ
ครับสวัสดีครับฮะ
เอาเรื่องถึงครับทั้งหมดเลยไหมครับ
จำไม่ได้
ครับ visual structure ออก
ฮะ
visual structure ออกไหม
ไม่ออกไม่ต้องจำสวัสดีครับ All right. Good afternoon, everyone. Welcome you to SCI33206. That's the section for M605. You have seen the energy level that is extended to the bigger atomic size. Okay, the atom that is greater than hydrogen. But it should have at least it should have only a single electron, and we can extend the Rydberg formula to the bigger atom version. Okay, it depends on the atomic number square, so Z square. โอ้ไม่ปิดอากาศอันนี้ด้วยนะครับ Okay, and the last one is the extension of the Bohr atomic radius to the bigger atomic size, to the bigger atomic size, and that's Rn is approximately 0.05293 divided by Z times n squared. Okay, n is the quantum number or state number of the electron orbit. In the first singly ionized helium, if you throw away an electron away, if you throw away an electron, you're gonna get the nucleus that has two neutrons and possibly two protons. Two protons and possibly two neutrons. Helium stays in gas phase, and it has hexagonal shells and noble gases. The atomic weight is 4.002602, and atomic number is Z equal to 2. If you find the energy in the ground state in the electron volt, you could compute from En equal to 13 0.6 minus 13.6 times because helium has 2 protons, Z will be number 2. And if you want it in the ground state, we're going to need to substitute n equal to 1. So finally, you will end up with minus 54.4 electron volt. Okay, you have nothing to do. Okay, 13.6 is already expressed in electron volt unit. And the next one is the radius in the ground state. Radius is computed from this formula 0.05293 divided by atomic number and the quantum number state with a power of 2 n squared. So n equal to 1 squared is going to be only number 1. You just divide this number by 2, okay, you get 0.026. But the radius is in nanometer, okay. The next one is the bigger atomic size, and that's lithium. You throw away 2 electrons. The remaining electron is 1. Okay. And in lithium, we have 3 protons. Okay, 3 protons. The atomic weight is around 6.93 until 6.99. And you're going to have lithium in solid state, solid phase. The number of protons is 3. That's why we have Z equal to 3. And find the energy of the first excited state in electron volt for the helium, for the lithium atom. We need to substitute Z equal to 3 and n equal to 2 because this is the first excited state. Once you substitute it, it's 3 squared because lithium has 3 protons, Z equal to 3. And after the calculation, we're going to get minus 30.6 electron volt. Regarding the radius of the first excited state, you're going to need to substitute again Z equal to 3 and n equal to 2 because this is the first excited state. If we say the ground state would mean n equal to 1. After the calculation, you get 0.07 nanometer. Anyway, both theory was planted by quantum mechanics, which is what we are going to see later. Let's consider this standard model for elementary particles. This table can be roughly divided into 2 groups. The first group is this one, quark electrons. This one is called boson, okay? And this part is called fermions. Fermions can be described by helical Fermi statistic. And boson is described by boson theory. The main thing that you can differentiate fermion from the boson is that the spin number of these particles would be 1/2, okay? But the spin number for a boson is not 1/2, not 1/2. It's 1, 1, 1, 1, 1, or even 0 in the case of Higgs boson. Now, let's get into the difference in fermion. You have, again, 2 groups, the violet group and the green group. The violet group is called quarks. The green one is called leptons. Quarks has the, of course, both have the spin number of 1/2, but quark has usually bigger more mass than the leptons. The chart of quarks and lepton are quite different. Okay, quarks would have the chart of either 2/3 or minus 1/3, but leptons would have the chart of -1 or +1 or even 0. 0 in the case of neutrino. Neutrino means neutral, right? Let's separate the first block in the quark. Okay, quark group. The most basic thing is up quark and down quark. Up quark has 2.2 mega electron volt per c squared. That's the mass. The down quark has 4.7. It's bigger. This has 2/3. This has the chart of minus 1/3. Once you accelerate the particle, you can get a bigger version, but the chart is the same. The spin number is the same. It's called sharp quark. The next one is top quark. It's even bigger than up quark and sharp quark. And regarding the negative charge, such as dark quark, if you accelerate the particle, you're going to get straight quark, or even a bigger version, which is called bottom quark. But these two things are not so permanently, are not so stable. In the opposite way, this is the positive charge. They are another group. That's called antiparticle. It has the same spin number, the same charge value, but it's in the opposite direction. It's negative. Okay, minus 2/3, minus 2/3, minus 2/3. This is minus 1/3. This is plus 1/3, plus 1/3. The mass is the same. You can see the difference is only the charge value. Basic version, bigger version, bigger version. That's everything about quark. Electron is the basic, the first electron that could be found in this table, or even in the fermion, right? The big version of electron is called muon. It has the same charge unit. It has the same spin number, but the mass is bigger. Tau has the same charge, the same spin number. It has even bigger mass. Okay, it has more mass. And the anti-version, we don't say anti-electron, but we would rather say positron. Okay, only particle that have a special or dedicated name. Okay, not anti-electron, but rather positron. Muon has its own antiparticle, which is called anti-muon. Tau has also antiparticle, which is anti-tau. Electron neutrino is the result from some decay. Muon neutrino could be a component to muon. Tau neutrino would be a component particle from tau. And the antiparticle version, because it has no charge, its own anti-version would have also no charge. It doesn't have charge at all. It remains neutral. The gluon, which the gluon doesn't have mass and charge. Gluon usually doesn't have any mass except for boson. Photon doesn't have any mass. Gluon doesn't have any mass. And boson is a little bit big. Okay, it's called Z boson, which doesn't have a charge at all. W plus boson has one charge, and W minus boson has negative charge, this antiparticle to each other, and the mass of W boson is the same. Okay, 80.39 gigaelectron volt per c squared. Okay. Once you know elementary particles, the basic particle would be the first one is proton, right? Proton is made of 2 up quarks and 1 down quark. Okay. These 3 particles are combined by the gluon. Okay. Gluon doesn't have any mass. Okay. Now let's move to the neutron. Neutron is different from proton because in the proton case you have 2 up quarks and 1 down quark, but it's not the case for the neutron. Neutron has 2 down quarks and 1 up quark, like this. Okay. Okay, now let's talk about wave-particle duality. This theory was created by a French physicist in 1924. His name is Louis de Broglie. Okay, he postulated that. Okay, we're going to see first the theory, which was created by his imagination, and later on, some scientists or physicists discover the realistic phenomenon that can confirm the theory by Louis de Broglie. Okay. Anyway, we will see first what is the theory created by Louis de Broglie. This theory is important because it gives us a new idea from what we have learned in physics. A free electron with a mass m moving with a speed v should have a wavelength lambda. And ขอโทษครับท่านอันนี้แป๊บนึงครับ should have a wavelength of lambda. And this wavelength is related to the magnitude of its momentum, P equal to mv. And this value is exactly the same way as the photon, which is described by lambda is h by p. Okay, de Broglie has learned the momentum theory, and he was familiar with the theory of the photon that has energy E equal to hf, right? Yeah, you just convert it to the momentum version. So this is the most basic of formula. Well, what is the idea behind his suggestion? He asserted that this relation holds also for many kinds of particles, such as electrons, protons, and all particles. Let the mass of neutron. We consider the first example about Louis de Broglie theory. The first one is mass of neutron, which is 1.675 times 10 to the 27 kilogram. Find the speed and the kinetic energy of the neutron that has de Broglie wavelength lambda equal to 0.2 nanometer. So we know lambda, we know the mass, and we're going to use the Louis de Broglie expression. Lambda equal to h by mv. When you want to know v, you just move v to the left hand side. Okay. Just move v. อันนี้ลบการ์ตูนคุณได้ไหม เนี่ยเอาไม่ติดปากกาหายไปไหนหมดครับห้องนี้ไม่มีปากกาเลยไม่ติดเลยนะ ไม่เป็นไรเดี๋ยวปากกาหมดเลย Lambda is h by p, right? Which is the lambda is equal to h by mv. So if you want to find v, so v will be h by m lambda. H is the Planck constant, so you get 6 times 10 to the 34. Divided by the mass of electron. Mass of neutron, sorry. 1.675 times 10 to the negative 37. Lambda is 0.2, right? So it's 0.2 times 10 to the negative 9. Harmonic. You'll get the result like this. Almost 2,000 meter per second. Regarding the kinetic energy, of course, when you know you can find the kinetic energy. 1 by 2 m v squared. 1 by 2 m, which is the mass, 1.675 times 10 to negative 27. V squared is the speed, which is what we have got before, 1977. 1977.9. Okay. 1977.9 square. You get the kinetic energy. With this value, 3.27, 10. Times 10 to negative 21 joule, right? And you need to divide it by, because the unit is not appropriate, we're going to convert it to the electron volt. You have to divide by the electron charge 1.602 times 10 to the 19. You're going to get 0.02 electron volt. Okay. So that's the kinetic energy. Now let's compare the Broglie wavelength for the electron case and the baseball. In electron case, it moves with the speed 10 to 7 meter per second. Okay. And the baseball case, you have the mass which is observable 0.145 kilogram, and it was pitched at 45 meter per second. Okay. So in order to compute the broad wavelength, you just use a straightforward calculation. H by MV, right? H is 6.626 times 10 to the negative 34, and here is 9.11, 10 to the negative 31, and the speed of the electron is 10 to 7. You get the wavelength on the order of 10 to the 11. That could be measured in really 7.27. And for the baseball case, you need to substitute the mass of the baseball and the speed of the baseball, which is much lower, 45 meters. 45 meters per second, and the mass of the baseball, you get 1.015. Times 10 to the 34. The wavelength on the order of 10 to the 34 is very hard to determine. So we cannot measure this wavelength easily, straightforward at the moment. But in the future, someone may be able to measure the wavelength on this scale. Now let's move to the second case, which is quite important, which is quite special, and that's the electron. Of course, you know that the bigger particle should move with lower speed. The very tiny particle like electron can move with high speed. For example, it moves with the speed of 0.999 C. What is C? The C is the speed of the light, okay, 3 times 10 to 8 meters per second. Okay, in this case, you cannot use the Lewis-de-Broglie equation immediately because the momentum is different. Okay, you cannot use P equal to mv anymore. The momentum now has to be moved to this idea. The relativistic theory, in the momentum case, we would have the relativistic momentum, and it's going to be P equal to mv, and there is denominator, which is denominator 1 minus v by c squared. Okay, if your v is the same as c, c by c will be number 1. 1 squared will be 1, 1 minus 1 will be 0. So momentum will be infinity, will be infinite. For the particle that has a speed the same as the light, so it's impossible because the photon doesn't have any mass. So when you have the C here, 0 by 0, so it's going to be defined as 0. But for us, in electron case, we can use this formula. Okay. And H mv H by P, right? This is the momentum in the relativistic case. You just shift this denominator to the numerator like this. Okay, and just substitute the mass of electron, the speed of electron, which is 0.999 of the speed of the light. And this is 0.99 the speed of the light is which is a constant. And you get 1.0858 10 to the 13 meter. This is quite measurable. Okay, this is quite possible to measure. And now let's consider the confirmation that could be found on Earth. 3 years later, Davidson and Gamer at Bell Telephone Laboratory discovered the electron diffraction. Okay, diffraction is a is a phenomenon, right, of the wave propagation. So when you discover this idea for the electron, it means electron should be have like a wave, right? In Germany, Esterman and Stern demonstrated the alpha particle would have also diffraction. Okay, not only electron, but also the bigger particle like alpha particle should have has also the diffraction. Diffraction, of course, is a kind of behavior in wave propagation. More experiments discovered that the diffraction of low energy neutron and large molecules could exist. So, yeah, you can see that the idea of Louis de Broglie, wave and particle, should be possible. All of this discovery give a strong support to the Louis de Broglie hypothesis. Because of this fluctuation, Werner Heisenberg developed a new inequality for the product of uncertain coordinate and the corresponding uncertain momentum delta p, okay, which can be written as delta x and delta p greater than h by 4p, or simply speaking, if you have a specific reduced version of the Planck constant, h bar is h by 2 pi, h by 4 pi, sorry, meaning 1 by 2, h bar, see, it's like, that's the same thing. This is h by 4 pi, or 1 half of the, it's less. The meaning from Werner Heisenberg principle is the following. Both momentum and the position of a particle cannot be measured simultaneously with arbitrarily great precision. This will limit the possible accuracy as in the classical physics would expect. Well, let's try to use the first version of the Werner Heisenberg uncertainty principle. Assume that we have a box of small size 10 to here. Okay, this is 10 to negative 10. meter. This is 10 to negative 10 meter. 10 to negative 10. Like this. So from inside this box, assume that we have electron like this. It moves inside this box. Estimate the minimum uncertainty in the x-coordinate of the electron momentum. Of course, in when Heisenberg uncertainty method, you have delta x, delta p greater than h by 4 pi. Right? Uncertainty of momentum, so it's going to be delta p. Delta p should be greater than h by 4 pi. Delta x, but the minimum value will be this one. This is minimum value. So delta p min will be h by 4 pi delta x. So it's time for you to substitute. You get 6 times 10 to 34, 444. Divided by 4 pi. Delta x is 10 to negative 10. And you can use the calculator to compute the minimum value. 5.27. to negative 25. Mass kilogram meter per second. The last one is the kinetic energy. Kinetic energy could be found also from the momentum, right? Because K is 1 by 2 mv squared. If you want to have it, it's going to be 1 by 2 mv. Right? But you have too much m. You have to divide at the end 1 by m. But this is p, right, which is momentum, so you can get 1 by 2 p squared by m. So momentum is this one right here. 5.27 times 10 to negative 25 square. Divided by the mass of the the electron, right? Mass of the electron, of course, is 911 times 10 to negative 35. Then you can use the calculator. You're gonna get the energy into 1.52 10 to him. 1.52 times 10 to negative 19 in joule, right? And you can divide this one by electron volt, right? You're gonna get the electron side. You're gonna get something in electron volt is 0.95, right? 0.